Earth and civilization as we know it has come a long way in the past 200,000 years and has experienced a multitude of changes in that time. The human species has only existed for a mere 0.0015% of the immense 13.7 billion year age of the universe. However, humanity has conquered some of the most daunting tasks in that time period. We have come from hunting and gathering in the fields of Africa to colonizing the entire planet in a time period that is relatively a blink of an eye on the cosmic level. Some of the greatest minds to ever exist have helped push modern civilization forward and achieve goals that were once thought to be impossible. In just the past 150 years, we have gone from being stuck to the Earth's soil to landing on our closest cosmic neighbor, the Moon. Humanity's success is nothing short of spectacular, but on the universal scale, we may be rather insignificant. What would happen if we met an advanced alien species with technology more advanced than we could ever imagine? In 1964, a Soviet astronomer by the name of Nikolai Kardashev introduced a hypothetical scale that could be used to measure a potential civilization's level of technological advancement based on the amount of energy the civilization can produce. It is known today as the Kardashev scale. The scale has three traditional types, but many extensions and modifications to the scale have been proposed since its creation. The scale is logarithmic, meaning, as we go on, the amounts of power the civilization has gets much more substantial. In 1964, Kardashev defined the three base levels of civilization based on the power available to them. Type 1, the smallest of the original types, is also called a planetary civilization. This is most similar to our good old friend, Earth. Type 1 civilizations are capable of storing and using all of the energy which reaches its planet from its host star, which, in our case, is the Sun. This amount of energy would amount to an enormous 7 times 10 to the 17 watts. Notice how I said most similar though, as our modern civilization here on Earth does not quite exactly fit into the Type 1 civilization category. Yes, I know, we pathetic humans can't even fit into the lowest level of the advanced civilizations. Rather than fitting into a Type 1 civilization, we humans lie in one of the extended types of civilizations, Type 0. You see, when this scale was proposed, famous astronomer and astrophysicist Carl Sagan produced a formula to define a certain hypothetical civilization's Kardashev rating. This is that formula, where K represents a hypothetical civilization's Kardashev rating, while P represents the amount of power the civilization uses in watts. A proposed Type 0 civilization will control approximately 1 megawatt, or 1 million watts of power, which is minuscule compared to the amount of power we use on a daily basis. In 2015 alone, the total world energy consumption was 17.35 terawatts, or this huge number. Plugging this number into P and cranking out the numbers, our Kardashev rating as a civilization would be approximately a Type 0.72. Even as a civilization with 7 billion humans on our planet, 12 of which ventured to the Moon, with spacecraft sent billions of miles into the abyss of interstellar space and plans to colonize Mars in the near future, we still only score a measly 0.72 on the Kardashev scale. According to Carl Sagan, humanity is going through a phase of technical adolescence, typical of a civilization about to integrate the Type 1 Kardashev scale. Michio Kaku, another brilliant theoretical physicist, suggests that humans may attain Type 1 status in the next 100 to 200 years, Type 2 status in perhaps the next few thousand years, and Type 3 status in 100,000 to 1 million years. This really goes to show the truly immense timescales it would take to advance to the next type of civilization. However, we are heading towards becoming a Type 1 civilization in the next couple hundred years or so, and this is a huge step for humanity. As a Type 1 civilization, we would have complete control over our own planet. Perhaps we could influence the weather, change the geological makeup of our own planet, and much more. However, even this amount of power is tiny compared to the next type of civilization, Type 2. A Type 2 civilization, also referred to as a stellar civilization, can control the total energy of its host star and transfer the energy throughout the entire solar system. One popular hypothesized device used to harness the entire energy output of a Type 2 civilization's host star are called Dyson structures. You may have seen these before, as they are rather popular in science fiction. The name was coined by Freeman Dyson, and is essentially a system of orbiting solar power satellites. Basically, it's an insanely massive hollow sphere built around a civilization's host star to milk all of the energy from it. Zephyrus made a great video on this idea, and you should definitely check it out. I'll be sure to leave a link to it in the description. But back on topic. Another rather exotic idea to harness energy for a Type 2 civilization would be to feed a stellar mass, for example, a star, into a nearby black hole and collect the photons emitted by the accretion disk. Now, how a civilization could somehow deposit a star into a black hole is beyond me, but it is a means of energy nonetheless. A Type 2 civilization would not only build these supermassive structures, but would control and live within them. They would control every single planet in their solar system, mine all the asteroids at their leisure, and essentially do whatever they want inside their solar neighborhood. The amount of power the civilization would have is remarkable, but is nothing when compared to a Type 3 civilization. A Type 3 civilization, also referred to as a galactic civilization, can control the total energy of its entire host galaxy. The amount of power this civilization would have is truly frightening, and is sorta in the realm of science fiction, but I'll cover it anyway. You see, this civilization would function extremely similar to the way a Type 2 civilization would work. It would harness the power of stars, mine planets and asteroids, and so on, but not only for one star, but for billions of stars. A civilization such as this would use planets and solar systems like Legos, building and deconstructing planets to build up their empire elsewhere in the galaxy. The galaxy would seemingly become their playground, and everything they do and use is merely a toy. Harnessing the energy of quasars would be like hitting the lottery for them. The supermassive black hole at the center of their galaxy could be used as an energy source for a Type 3 civilization. Galactic real estate would become a reality, with planets, stars, or even complete solar systems being auctioned off by some supreme leader. Interestingly enough, this hypothetical galaxy may not even be noticeable. If such a civilization did exist, all of the energy from the stars would be held and used for whatever the civilization may need. This means all the starlight, gas, and elements in an entire galaxy would become like your kitchen pantry. If all of the matter in their entire galaxy was exploited for energy, an outside observer would view the galaxy to be completely invisible. It would appear as if there were a hole in the galaxy, or, if they have colonized the entire galaxy, perhaps nothing at all. There is a place in space known as the Great Void. At nearly 330 million light-years in diameter, the Great Void is one of the largest known voids in the entire universe, and is commonly referred to as a supervoid. This region of space is seemingly devoid of life and galaxies as we know it. A region of space with such a massive size as the Great Void contains, scientists estimate that there should be at least 2,000 galaxies in this area of space. But, to date, there have only been 60 galaxies that have been discovered in the Great Void. This is a mere 3% of the amount of galaxies that should occupy an area this large. So, where are they? Could it be Type 3 civilizations completely dominating an entire region of space, milking a 330 million light-year wide region for resources? Leave your thoughts in the comments below, and I'll be sure to respond to them as quickly as I can. Thanks for watching. In 1970, a British mathematician named John Conway created a project known as the Game of Life. Even though it's a game, it isn't one that you necessarily play. The Game of Life is a zero-player game, which doesn't make much sense when you hear it. The way it works is, you put in a set of initial conditions and then observe. That's it. Once you put the initial conditions in, the game runs itself. Other than the small set of rules that the simulation follows, it runs on almost nothing. Some patterns only run for a few generations before they die out, while others seemingly go on forever. And this got me thinking, if a simulation as small as this, with very little variables, can result in something huge, what if we scale this up to, say, the size of a universe? A simulation that's more than just dots on a screen, but a simulation with galaxies, planets, and life. More importantly, if that is possible, how do we know that we aren't living in one of those simulations right now? At first, the argument for our universe being a simulation just sounds like complete nonsense. But when you actually take a look into it, it seems to become more and more plausible. How do you observe things? Well, you see them, or smell them, or observe them with any of your senses. This is your subjective reality. A reality based on a subject. You.
You are alone in your own head. Everything that you observe or interact with ends its journey with neurons firing in your brain in a certain way to create your view of the world. With this being said, can you prove that there is an objective reality? That is, a reality that exists independently of our knowledge of it. A sort of overarching reality that encompasses all of our subjective realities. It exists without our observation of it. That sounds kinda confusing though. You can't know that an objective reality exists without someone or something to observe it. For example, if I went outside and stated that it was freezing, and you went outside and stated that it was scorching hot, that is where our subjective realities come into play. From this, it seems that two different minds, two different people, can observe a single object in multiple ways. In an objective reality, it would just be either freezing or just scorching, regardless of either one of our observations. In an objective reality, in order to prove something exists, you would have to observe it without observing it, which is an obvious contradiction. This kinda begs the question, can you prove that anything outside of your own mind is actually real? Babies aren't exactly the smartest things in the world, but they do give us a good insight into how we learn, how our minds develop, and how we become aware of the world around us. If you look outside your window, you might see a tree, or another house, or maybe your car in the driveway. But you don't need to physically look out there to know that those things exist. This is known as object permanence. It is the knowledge that objects exist even when we aren't perceiving them in any way. However, we aren't born with this skill. It's something that is developed over time. I'm sure you've seen or even played peekaboo with a baby before. When you cover your face, babies less than about a year old will believe that you disappeared into thin air. But when you take your hands away, you're back into their reality. The knowledge that things exist even when you can't observe them isn't learned until about 1.5 to 2 years into life. But is that actually true? This goes back to your subjective reality. Sure, after a while you might learn that some things seem to exist when we aren't observing them, but how can you be certain? At the end of the day, it is just your subjective reality. It's due to your consciousness that you can even observe anything. Take this for example. When you look at your computer or phone or television or whatever device you're watching this on, you know that all of those things are composed of atoms. But you can't really see them, can you? It's not until we take a device such as a microscope to observe them that we can actually see these atoms that make up everything. We can't see them until they're observed closely. So if this is true, this can make simulating a universe 1,000,000 times easier. Simulating an entire universe with billions of galaxies over billions of light years would take up a lot of computing power and would really just be a waste. All a post-human species would have to do is just simulate the consciousness of its subjects. Or maybe even subject. Is there any way to prove that anyone you talk to on a daily basis isn't just another function of code in the simulation? All the simulation has to do is just trick you into believing the world around you is real. When you play video games, you'll notice that things don't render in completely when you aren't looking at them. It's a waste of power and energy. Since video games are basically simulations of our own, why wouldn't a simulated universe follow a similar strategy? It's a very arrogant statement coming from a human, but hear me out. If a tree falls in the forest and no one is around to hear it, does it make a sound? It's a pretty popular psychological question, and it fits really well here. In a simulated universe, if no one is around or conscious of that even taking place, there's no reason for it to make a sound, or for the tree to even fall in the first place. If we stumbled upon that tree later on, it would just be lying on the ground to give the illusion that it fell. If we aren't observing galaxies in the Hubble Deep Field, what's the point of them existing in the simulation at all times? It could be possible that just bits and pieces of what we call the universe exist and are observed at a single time. If we look back at where technology was 100 years ago and compare it to now, you can see an obvious difference. If technology continues to advance at any rate that's greater than 0, then it is possible that in the future, whether it be 100 or 1,000,000 years, that we will eventually have technology with near unlimited computing power. But all I keep talking about is power and energy. How would a civilization even get this kind of power? Remember those creepy Russian dolls that when you open them up, there's another doll inside, and then another and another? There's a concept that's basically that, but on a stellar scale. Take our sun for example. It's really big and really hot, and it radiates a ton of energy. If we could somehow harness all of that energy, we could use it to simulate millions of universes simultaneously. But how are we supposed to gather all that energy? using a little something called Matryoshka brains. If an advanced civilization was able to build a megastructure encompassing the sun in multiple layers, just like the dolls, they would have all of the sun's energy at their disposal. A civilization capable of this could most likely do this with multiple stars, and thus will be able to simulate as many universes as they'd like. We can run simulations on our own computers that project our universe on a large scale. The Illustrious project does this very well. Just like the Game of Life, the project is much like a zero-player game. The scientists who created the project gave it certain properties that match our universe near the beginning and then just let it run. It's able to project our universe on a large scale very accurately, actually. And that's just with the computing power we have today. In the future, simulations like these will get more and more accurate until eventually, it may even be realistic. However, it cannot be perfect. When we observe atoms and attempt to view electrons or other particles, we cannot know both the position and momentum of these particles with 100% certainty. This is called the Heisenberg uncertainty principle. There's a limit to what we can know about the mass, energy, position, and time of a particle, meaning that in any simulation, there is no way to accurately represent everything exactly as it was. You can never truly have a perfect simulation of reality. It will always be slightly slower than the actual reality itself, even with an infinite amount of computational power at your disposal. In order to combat this, limits have to be put in place. Tricks and sleight of hand have to be used. A good example is this. If you have an old computer and try to run the newest games on it with 20 Google Chrome tabs open while also listening to music, you'll see an obvious decline in your computer's performance. The old computer doesn't have the computing power necessary to handle all of that strain, so it slows down. Now, think of black holes. When you're around that much matter in one place, that much information in one spot, time literally slows down. It's as if whoever created the simulation slowed down parts of the simulation to keep the energy required low. Could this be an explanation for the speed of light? Could this be the speed of computation of whatever simulation we may be in? There's no way to tell, and all of this is theoretical, and to be honest, insane. But it doesn't mean we shouldn't think about it. It could actually help answer some of the most sought out questions we ask. For example, the Fermi paradox. When we look out into the universe, we don't see any other signs of life. Are we really alone? Are we just a glitch in the simulation, or are we just not looking hard enough? Take the creatures that exist at the bottom of our oceans. Are they aware that we humans even exist? Are they aware of anything outside of their immediate vicinity? Do they know that they're living on a big rock floating around a hot ball of gas orbiting some big black hole of death in the center of the galaxy that sucks anything and everything in? Probably not. What if we're just like those creatures, but the furthest that we can observe or are aware of is what we call the observable universe? Perhaps the universe cannot exist without conscious minds to observe it. The idea of simulated universes could also explain the multiverse theory. The idea of a multiverse is just that, multiple universes, or perhaps infinite universes. In many situations, when there's a high chance of someone getting killed or someone has a near-death experience, they are reported to have said that their life flashed before their eyes. Their most special moments and memories from their life all comes rushing back to them in an instant. Researchers from Hadassah University in Jerusalem analyzed multiple cases of people who experienced these near-death experiences. In almost all of these cases, those being interviewed stated that they had lost all sense of time. One of them wrote, "There is not a linear progression, there is a lack of time limits. It was like being there for centuries. It happened all at once, or some experiences within my near-death experience were going on at the same time as others, though my human mind separates them into different events." Another respondent stated, "I could individually go into each person and feel the pain that they had in their life. I was allowed to see that part of them and feel for myself what they felt. When people experienced these things, it was as if they were living another life. They experienced things they never felt before. It was as if they stepped foot into an alternate reality. The idea of time didn't exist for a short while, and they were able to analyze things that no other living person could do. When you're talking with a friend and have that weird deja vu feeling that you've had the same conversation before, or that you've experienced exactly what they're feeling without actually having been through it. Perhaps you, in another universe or another simulation, actually had that same thing happen to you. The illusion of free will allows us to live our lives in any way we see fit. But what if every single decision that you've ever made has been pre-programmed into the simulation that we could exist in? Every decision you make branches you off into a parallel universe, a parallel simulation, where every choice that you have ever made has led you to this exact very moment. At home, on your phone, watching this very video. Current technology already greatly surpasses human performance and speed. That's why many big companies like Tesla use robots and other machines to do jobs that humans can't do as effectively. Biological neurons, those are the neurons that fire in your brain every second of the day, operate at a peak speed of about 200 Hz, whereas modern microprocessors operate at least 2 GHz, a whole 7 orders of magnitude faster. Even with modern technology, a super intelligent AI, for example, a human mind that runs on hardware faster than the brain, could make decisions millions of times faster than current humans would. It would be able to think of every outcome and pick from the best ones. However, we are not super intelligent AI. There is a limit to what the human brain can do, can observe. We have, though, made some very important discoveries that keep us asking questions. Most importantly, math. Math seems universal. There are numbers and patterns in things from the size of atoms to things the size of galaxies. Discoveries that we humans have made in only the past couple thousand years have allowed us to ask crazy questions like, are we living in a simulation? If we were to put every single one of the possible billions of simulations into a hat, jumbled them around and picked one out, what are the chances that we will grab the original one? The one who made all the simulations in the first place? What are the chances that the Earth we're living on even exists? Perhaps an advanced alien species came upon our dead planet after billions of years and found traces of our DNA, traces of our existence, and then made a simulation out of that to learn about the history of the barren wasteland of a planet they had just stumbled upon. If that's the case, then hello. We can never know for sure. All we can do is observe and hope that our game of life is one that we can win.
Meet Arthur. Arthur is really good at math, and he always has been. In fact, he planned on going to college to study math, but recently, life didn't pan out the way he expected it to, and so he's not quite where he thought he would be by now. Sounds like most of us. What is more probable? 1. That Arthur is a lifeguard at the local beach, or 2. That Arthur is a math tutor at a local school and a lifeguard in his free time. The correct answer here is 1, that Arthur is a lifeguard at the local beach and only that. Now don't worry if you got it wrong, the majority of people do, even people with years of experience in statistics. If you chose 2, the error you made is known as a conjunction fallacy. You see, even without knowing anything else about Arthur beyond what the problem tells us, we can be certain that 2 is less probable than 1. Why? Because it's more specific, meaning it involves the probability of Arthur being a lifeguard and the probability of Arthur being a math tutor in conjunction. You may find it easier to visualize using a Venn diagram like this one. Questions like this one were developed in the 1980s to test cognitive biases, among other things. Why is this important for this video, though? Because it offers a general statistical insight that is relevant everywhere else as well, even, as you will see, in the deepest trenches of reality. The insight is simply that more specificity is less likely. The scenario of Arthur being a lifeguard and a math tutor may seem more likely, given how I've intentionally described Arthur to be mathematically inclined. But no matter how mathy he might sound, option 2 is the more specific scenario of the set, meaning more things have to go a certain way for it to occur, and it's therefore less likely. For a more drastic example, which is more likely? Getting struck by lightning, or getting struck by lightning and getting hit by a car in the same day? Now, onto the deepest trenches of reality. Have you ever wondered why most of the processes that go on in our lives are so seemingly irreversible? Why do they tend to go one way and not the other? Why is it that sugar can be stirred into a cup, but when you move your spoon the other way, it never unstirs itself? Why is it so that the sock drawer always needs to be organized by someone and never does so on its own accord? Why is it that a cup of cold water doesn't suddenly start boiling? These questions might seem unwarranted, and even dumb. We have so much intuition for these things that it almost seems unnecessary to ask these questions to begin with. But the reason why they need to be asked is because there's actually nothing in physics, no law or theory, that is against these processes reversing themselves. Laws that are obeyed when a cup of warm water cools down are obeyed just as well as when it heats up. So there must be something else that's tipping the balance almost. Something that almost wants gases to disperse through a room. Something that wants that cup to go cold. That thing is known as entropy, and it may have more to do with probability than with physics or chemistry. But first, let's try and understand what entropy means. You can understand a lot about a concept just by thinking about how it was named. The term entropy was coined in 1865 by Rudolf Clausius, who used it to define the second law of thermodynamics. However, it's much better if we try to understand the term using classical languages. The Greek word for entropy doesn't necessarily refer to disorder like you might expect. Rather, it talks about isotropic turning, meaning same no matter how you turn it. It's talking about the number of ways you can change something, or transform something, and still have it look the same. If you want to think of it in simpler ways, think of a disorganized desk. There are some ways in which you could organize a desk, and you can directly specify them, since an organized desk refers to a particular arrangement of things in a particular way. When it comes to a disorganized desk, there's really no rule that needs to be followed. A desk can be disorganized in so many more ways. Of course, a stash of papers on the left might look different than a stash of papers on the right, but in the grand scheme of things, it's simply disordered, especially when that's the only distinction you're drawing, one between order and disorder. Now, these things might seem simple enough, but there are certain missing links we need to address before we jump from an analogy like that to reality. First, let me remind you of what we just talked about at the start of the video, that more specificity is less likely. If we use that in the desk analogy, it means that since an organized desk is a comparatively more specific arrangement, it is less likely than a disorganized desk to occur just by random chance. I'm sure you have some intuition for this. If you organize your desk at the start of the week, unless you do something to maintain that order, it's probably not going to stay very ordered as the week goes on. Another missing link is the fact that in reality, things aren't super distinguishable. Particles at the atomic level are much harder to tell apart than the things on your desk. Even if certain disorganized versions of your desk might look different to you, you can rest assured that that won't be the case when you're looking at a million particles that all look the same. But arguably the biggest link that makes entropy a hard concept to digest is the scale of things. You and I really have no clue, and I mean it when I say it, no clue as to the real size and number of things. Of course, you've heard things about there being more stars than grains of sand and whatnot, but you really don't know how big it is. The term unfathomable gets thrown around quite a lot, but rarely is its use as fitting as it is now. Reality is unfathomably complicated. Even if you measure complexity just by the number of particles, you and I will fail to internalize the sheer size of things no matter how much we try. But I'm gonna go ahead and try anyways. Let's look at a box with 2 compartments and a few balls in them. Let's start nice and easy. So we have 2 identical balls. We allow the balls to move freely in between the 2 compartments. At any given point in time, where could the balls be? Well, they could all be in the left compartment, that's scenario number 1. Or one ball could be in the left and the other could be in the right. That accounts for 2 scenarios actually. Since there's 2 identical balls, if we were able to swap them in this arrangement, we wouldn't be able to tell them apart. Or they could all be in the right compartment, the 4th and final scenario. All of these situations are equally likely. Now, what is the probability of finding both balls in the left compartment? Only 1 out of the 4 possible scenarios meets our requirement, so it's going to be 1 out of 4, or 25%. Now, let's bump it up a bit. Instead of having just 2 identical balls, let's have 4. Now, since there's more balls to move around, the number of ways they can be arranged also goes up. This can be represented by 2 to the power of the number of balls. In this case, 2 to the power of 4 is 16. Subsequently, our luck needs to be that much better to have all the balls spontaneously place themselves in the left compartment. And sure enough, the probability of having all 4 balls in the left compartment is now down to 1 in 16. Let's keep going. What happens when we have 5 balls? The probability goes down to 1 in 32. What happens with 16 balls? The probability goes down to 1 in 65,536. Notice how quickly the numbers jump up. Let's jump ahead a bit. What happens with 128 balls? Which is still a pretty good number, we can still kind of visualize that. The probability is now down to a staggering 1 in whatever this number is. Now let's take a step back to put things in perspective. We rarely have these well-defined compartments in reality. Things move around wherever they want to, and so the number of ways in which they can arrange themselves, even with two balls, is, and I'll say it again, unfathomably large. But that's still with just two balls. Remember earlier in the video I said it would be hard for you to distinguish between particles when you're looking at a million of them at once? Even a million particles is such a gross underestimation of reality, it's not even a contest. Something as little as 20 milliliters of water, basically the last sip of water in a bottle, has not a million particles, not 10 million, not even a quadrillion particles. It has over 10 sextillion, or 10 to the 23 particles. I'll spare you the math on this one, but let this be the takeaway. Things get really complicated really fast. To connect the dots with our other takeaway, in reality, an ordered arrangement of particles, such as gas that is not dispersed, or sugar that has not been mixed, also is significantly more specific when compared to other disorderly arrangements, like the desk example. That specificity makes it so much less likely. There's that many more particles to arrange, there's that much more luck needed for an orderly arrangement to exist. When you put all of that together, it starts making sense why things tend towards disorder. It's not so much that the laws of physics are biased towards one arrangement or another, rather, disordered arrangements are so overwhelmingly more likely than ordered arrangements, that if you let nature do its thing, things will always become more and more disordered. It's remarkable that, at the core of it all, it's not a law of physics or chemistry, but rather one of probability. Interestingly though, this can lead to the curious insight that it is indeed possible for a cup of water to spontaneously go from cold to hot. If the trend towards disorder is indeed independent of the laws of physics, there should be no problem with that happening. And in reality, there really isn't. Why don't we see it then? Well, the scale of things comes into play again. Going back to the ball compartment example, even if, say, we reduce the number of balls back to 1,000, and say that the balls change to a different arrangement a million times a second, we would still have to wait 300 quadro-nonagentillion years to see them all in the left compartment. That's many more orders of magnitude than the age of the universe, all for something as simple as 1,000 balls being put into a box. It's fair to say that it wouldn't be very wise to wait for that to happen. But what if you did? What if you saw out all of the arrangements of everything in the universe? Well, that brings us to the power of entropy and giving us an insight into the end of existence. You see, energy that we can use often needs to be in a particular form, in an ordered form. You can think of it in terms of food. Foods are just molecules, and everything has molecules. But you just can't eat everything. You can only eat things in which those molecules are arranged in very particular ways. In any other disordered arrangement, energy simply isn't very useful. And across the universe, energy is constantly transitioning from an ordered to a disordered form, causing a loss of useful energy. This sort of a progression also implies that at the start of the universe, energy was probably very ordered. But what must have got it there? Was it just a fortuitous ordering of particles? And what happens if this process keeps going on? Well, the most likely outcome is what is known as the heat death of the universe. As the arrow of time pushes us forward, each day the universe inches closer to maximum entropy, a state of no thermodynamic free energy. It doesn't necessarily mean that the universe will be hot or that it'll be cold. It just means that once everything has equalized to disorder, there will be no temperature difference to motivate a thermodynamic process to occur. Nothing changes. Nothing happens. Time ceases to have any meaning. This gradual process is inevitable, but it is nonetheless hard to see. The universe is hardly distinguishable from one day to the next, so to imagine that it might all one day simply cease to exist is a bit hard to wrap your head around. But that's not to say that we're so oblivious to the regularity of decay. It's all around us. Fading memories, aging, death, and the ultimate impermanence of our existence repeatedly remind us of decay. But if it's all so inevitable, what's really the point of it all? Why even bother? In his book Enlightenment Now, Steven Pinker says, "The second law of thermodynamics defines the ultimate purpose of life, mind, and human striving, to deploy energy and information to fight back the tide of entropy, and carve out refuges of beneficial order. An underappreciation of the inherent tendency towards disorder, and a failure to appreciate the precious niches of order we carve out, are a major source of human folly. Maybe it really is just that. Small moments of apparent order against an inescapable reality of decay. But eventually, the lights have to go out one last time. The heat death of the universe is still a theory. It's a theory in a sense that we would have to cycle through all the different ways in which things can arrange themselves. And while the sheer numbers and timescales involved are too large for a human lifetime, that's not the case for the universe. The universe has time, and in a sense, is time. What is to say that in doing so, and going through all the different combinations, we won't stumble upon an orderly arrangement again? Sure, it might take many quaternonagentillion years for something like that to happen, but it can happen. The possibility is vanishingly small, but it remains non-zero. And when that does happen, the lights just might turn back on. And for all we know, we might just end up back at square one. $13.8 billion years. That's how long the universe has existed. Older than the planets, stars, as old as time itself. The universe is immeasurably vast. To put it into perspective, if we reduce that timescale down to a single year, the entirety of recorded human history, you, me, and everyone else who has ever lived, would take up a minute at best. Our lives, the long decades of joy and sorrow, pride and regret, every dreary morning and sunny afternoon, would represent around 1/5 of a second. This cosmic calendar, first popularized by Carl Sagan in the 1970s, is meant to show us just how precarious our position is in the universe. We have not been here long, and if the last few months of life on this cosmic calendar are any indication, we won't be here much longer. Over the past 4 weeks, our planet has been wiped clean of life nearly 6 times over. Of all the billions of species to ever exist, more than 99% have gone extinct. It would probably be a little arrogant to assume that we, who came along only a few minutes ago, are somehow different from all those who came before us, that our species could and should be the first to endure past our time. But the fact that we're even talking about this at all suggests that maybe we are different. We built telescopes, searched the stars, and pieced together the story of our universe. We engineered tools, dug pits, and unearthed the stories of our ancestors. And in all that searching, we found no sign that there's ever been anyone or anything like us. The fact is, humans are adaptable. Most humans are uniquely suited to the environments they evolved in, and if their habitat changes, they don't change with it, they go extinct. Humans are different. When it gets cold, we don't freeze. We knit ourselves sweaters and light a fire. When it rains, we aren't swept away by the flood. We build barriers and divert rivers. The list goes on. Forests burn and we douse the flames with water. Earthquakes topple cities and we rebuild them stronger. We've gotten so good at adapting to our surroundings that at this point, most natural disasters don't pose much of a threat to our species as a whole. But what couldn't we withstand? What, if it happened tomorrow, could end the human story instantly and infinitely? These are the biggest threats our species faces, the threats which seek to make us history, like the 99% who came before us. These are the most dangerous things in the universe. There are many theories as to how the universe might end, and all of them posit that we won't be around to see it happen. One theory suggests that the universe, which once began by expanding ever outward from a single point, will continue to do so for all time. The evidence for this is clear. Every day our own Milky Way galaxy grows more and more distant from the neighboring galaxies as the space between them expands, so it makes sense to conclude that then, eventually, they'll disappear from our view altogether, leaving us alone in the dark. We can live like this for billions and billions of years. The galaxies, though spread apart, will hold together. But eventually, the stellar nurseries which add new stars to our galaxy will run dry. The remaining stars will age and burn into nothingness, leaving only black holes to suck up everything that remains. A hyper-advanced civilization could cobble together distant stellar remnants to create new stars, but in time, these too will run out. There will be no material left for us to use, no energy to sustain us, and eventually, the black holes will decay too. This is known as the Big Freeze, and it is one threat we cannot escape. While the galaxies are, on the whole, growing apart, there are a few exceptions. 2.5 million kilometers, or about 1.5 million miles from us, lies the Andromeda Galaxy, and it's on a collision course with the Milky Way. In 4.5 billion years, this collision will tear both galaxies apart. Surprisingly, this in itself won't hurt us. On a cosmic scale, the stars and planets of our two galaxies are actually so distant from one another that no star will directly collide with another. Black holes, however, are a different story. They can grow far, far larger than any star, in almost every spiral galaxy, including Andromeda and the Milky Way, holds one at its core. If our sun comes too close to either one of these supermassive black holes, we'll be consumed or, at best, ejected into interstellar space. While we already know about the eventual death and rebirth of our galaxy, there's one smaller, more local danger that could threaten our solar system in the same way: the appearance of a rogue black hole. Black holes form when a massive star runs out of fuel at the end of its life cycle. Unable to burn as hot as it once could, the star can no longer support its own weight, so it collapses inward until the gravity is so great it warps the fabric of space-time itself. While black holes normally stay in the same place as their original star, violent stellar events like the merging of two separate black holes can send them hurtling out into interstellar space at incredible speeds. It's not easy to spot objects drifting in the lightless voids between stars, and an object that absorbs light itself is even more impossible to spot. If one wandered close enough to our sun, its massive gravity would disrupt the orbits of every object in the solar system, slowly but surely throwing the planets into disarray. As it consumes the planets and asteroids in the outer solar system, it'll only grow larger, until finally Earth gets caught in the path of the singularity. After stripping the planet of its atmosphere and us along with it, the black hole's gravity would create tidal waves as large as Mount Everest, stretching the Earth's crust like a ball of dough until finally, the tectonic plates rip apart, exposing our planet's molten core. As we pass the event horizon, everything that was once our home will be crushed into rubble, then dust, then atoms. In this scenario, the best strategy would be to move ourselves. There are millions of potentially habitable worlds in our galaxy alone, and by establishing settlements there, we give humanity a backup plan, saving us from being done in by any one galactic calamity. This is the same strategy we'd use to avoid extinction through the expansion, contraction, and eventual death of our own sun, which will inevitably cook and consume the Earth just as readily as a black hole would. The hardest threats for us to avoid are those that could happen at any time without very little warning: gamma ray bursts and asteroid impacts. While neither of them would destroy life on Earth forever, they may very well destroy us completely. We know this because they've wreaked havoc before, causing 2 of the past 5 mass extinction events in our planet's history. Gamma ray bursts are massive blasts of electromagnetic radiation emitted by collapsing stars. They emit so much energy that, for the brief moment of their existence, they're brighter than every other star in the universe. If the Earth happened to be squarely in the path of one of these narrow bursts, the effects would be immediate and terrible. 75% of the upper atmosphere, specifically the ozone layer, destroyed in an instant. Without ozone, all life on Earth would be exposed to the harsh ultraviolet radiation of the sun, causing DNA damage and cancers. The long-term effects are even more devastating. For several years, acid rain would fall and photochemical smog would darken the skies, reflecting more of the sun's rays. If this were to happen today, given how unstable our climate currently is, the darkness might trigger a runaway cooling effect, leading to a decade-long winter. These same effects were seen during the Cretaceous Paleogene extinction, or the death of the dinosaurs. Approximately 66 million years ago, a 10-kilometer or 6-mile long asteroid struck the surface of our planet, carving a near 180-kilometer or 112-mile long crater in present-day Mexico. The impact instantly vaporized the water beneath it and scattered hot debris across the planet, setting the world aflame. Soot from the blast turned to aerosol and blackened the skies, causing a very real decades-long winter that slowly killed off all the life on the surface. While humans today might survive such an impact by hiding away in a remote underground bunker, the vast majority would be left to die. If an even larger asteroid struck, say, 30 to 60 kilometers, it would completely eradicate all life on Earth, no matter the hiding place. Essentially, if an asteroid or gamma ray burst aimed itself at Earth, there would be very little we could do about it. as gamma ray bursts are impossible to predict, our only immediate solution would be to deal with the effects as best as we can. Unlike gamma ray bursts, which occur in our local group of galaxies only once or twice every 5,000 million years, rogue asteroids are a real and present threat, and the only one that humans have so far taken steps to counter. Since the 1990s, NASA has identified over 25,000 near-Earth asteroids. While many smaller ones may be out there, they've located more than 90% of the asteroids large enough to devastate the Earth. While no large asteroids are currently on a collision course with our planet, NASA scientists have proposed and even tested a solution to counter them. In September 2022, NASA deliberately flew the Double Asteroid Redirection Test Satellite, or DART, into the asteroid Dimorphos, measurably changing its orbit. Should a world-ending asteroid come barreling towards the Earth, we'll simply nudge it out of the way long before it ever reaches us. While the dangers we've discussed so far are possible, inevitable, and devastating, they only come along every 100 million years or so, if that. The odds that one will happen in the foreseeable future are slim to none. In that sense, the most dangerous thing in the universe isn't simply that which could cause the most destruction, but the one that's most likely to. For that reason, we are the most dangerous thing in the universe, at least to ourselves. If we are to die, the odds are overwhelmingly clear that it will be at our own hands. There will be no death from above, no gamma ray burst or rogue black hole. It'll be because we chose to die, either through the negligence of human-caused climate change or the short-sighted malice of nuclear war. We invented the machines that warmed our planet, causing droughts, floods, and massive storms. We invented the bombs that can annihilate millions in an instant, and each day we choose to keep them armed and aimed squarely at our own heads. At this moment, there's over 12,000 active nuclear warheads on our planet. A full nuclear exchange will instantly wipe out entire cities, and in the aftermath, radioactive fallout will eventually kill billions. The skies will darken and plunge our planet into a nuclear winter, slowly starving everyone else unfortunate enough to survive, just as it happened 66 million years ago and 400 million years before that. The Bulletin of Atomic Scientists keeps a symbolic clock that measures humanity's proximity to doomsday. In 1947, when the clock was first unveiled, an expert panel of scientists and academics judged that we were 7 minutes to midnight to our own extinction. When the Soviet Union fell, ending the Cold War, they turned the clock back to 17 minutes. But now, as we fail to deal with climate change, as nuclear arms treaties fall apart, and as Russia once again threatens war with the West, we're 100 seconds from midnight. At this moment, we have two paths forward. We can listen to our collective inner voices of reason and survive our own present together, or we can all join those who went before us, only this time, our extinction would be by our own hands. Imagine living a life filled with happiness and pain, love and grief, ambition and despair. A life with parents, kids, grandkids, and ultimately, the death of everyone, including yourself. And then it all happens again in the same way. You make the same choices, the same people die in the same way, and your reaction is the same. I'm describing the existentialist philosopher Friedrich Nietzsche's concept of eternal recurrence. It's a hypothetical notion he put forward as an exercise in overcoming yourself to affirm all of life. In order to become who you are and realize your full potential, you need to confront the limiting aspects of your character. Eternal recurrence was meant to be an excruciating thought, but many people have interpreted it as the opposite. Some of us find the idea of re-experiencing our lives to be exciting. We cling to our experiences and our consciousness. We hate the idea of letting our lives go or losing our cherished memories. Similarly, the idea of rebirth in Hinduism and Buddhism get people excited. We want our consciousness to live on, even if it's in another body. In both of these religions, the idea of rebirth isn't supposed to be positive. You're supposed to work towards ending the cycle of rebirth by embracing the principles and practices of Hindu and Buddhist thought. Until recently, this notion of rebirth had some cosmological relevance in the theory known as the Big Crunch. The idea is that the expanding cosmos will eventually collapse back into itself and reform into a singularity that could spark another Big Bang. In this process, instead of the universe expanding forever, it would reach a point where its size would start to decrease. This would eventually cause gravity to become the dominant force. The universe would shrink and eventually collapse onto itself, and the cycle would continue over and over again, a cyclical rebirth of the universe. It's an idea that sparks hope that life could begin again. We wouldn't be left with a cold, empty universe, and maybe our consciousness would be reborn again somehow in this process, just like in Nietzsche's hypothetical concept. Trillions of years from now, we will live on. Sadly, this theory of the universe isn't the most likely according to modern physics. In the late 1990s, astronomers studied 42 supernovae. These are white dwarf stars that siphon gas from a companion star. The increase in mass causes a runaway nuclear reaction that ultimately leads to a very bright explosion, a supernova. After studying these supernovae, they discovered something that would change how we understand the universe. Distant supernovae were dimmer than they expected. Why does this matter? Well, if the expansion of the universe was slowing down, as we formerly expected, then the supernovae would be brighter. But the fact that they were dimmer meant that the universe's expansion is actually speeding up. This speeding up went against our understanding of gravity in the universe, so either Einstein's theory of gravity is wrong, or there's something else at play. Some new components in the universe that we hadn't accounted for. That something is a force called dark energy. Dark energy is believed to be virtual matter that pops in and out of existence. It doesn't interfere with energy conservation, and instead of pulling like gravity, it pushes. According to astronomers, the universe is made up of 69% dark energy and 26% dark matter, both of which are invisible. Everything we can see, like the stars, planets, all the trees, places, and people that have ever existed, only make up 4.9% of the universe. The remaining 0.1% are neutrinos, and 0.01% are photons. The force of dark energy is believed to be a constant, expanding the universe continuously without stopping or regressing. The impact of this dark energy is that the expansion of the universe will never slow down. Eventually, the universe will expand so much that no distant galaxy will be visible from our own Milky Way, and by then, our galaxy would have merged with the neighboring galaxies. The end result here is what's known as the Big Freeze, or the heat death of the universe. Due to the endless expansion, all heat will be distributed evenly across the universe, leaving the cosmos in a final resting state at just above absolute zero. Entropy is the measurement of everything in the universe moving from order to disorder. According to a thermodynamic principle, entropy will increase until it reaches its maximum value, and when entropy has reached this value, all the heat in the universe would have been evenly distributed. There will be no more room for usable heat energy, and once there's no heat, there is nothing. Star formation will have ended long before this. The universe would be so vast that its gas supplies would be spread too thin for any new stars to be born. Galaxies will be gone and all matter will be locked inside black holes. Eventually, even the black holes will disappear. This dark era will last way longer than any other period of the universe. Time will be almost infinite at this point. Time began with the Big Bang, and it likely ends with the Big Freeze. Mechanical motion in the universe will cease altogether. Nothing will ever happen again. The universe will effectively be dead. But is this heat death a sure thing? Just like everything else, not exactly. The assumption the Big Freeze makes is that the force of dark energy is a constant, but according to our best measurements, there's a bit of uncertainty about whether dark energy is a constant. It's also possible that the force of dark energy will just eventually change. Dark energy could become stronger, and even if it gets just a bit stronger, it could lead to another theory of the universe's end, the Big Rip. This is where the pull of the universe's expansion becomes stronger than the gravity it contains. This would effectively tear the visible universes apart, including galaxies, stars, black holes, and planets. The universe would be left with disconnected particles, somewhat reminiscent of the way heat energy is evenly distributed in the Big Freeze. Dark energy could also become weaker. Gravity would then win its struggle with the dark energy, and the universe would collapse, and this becomes the Big Crunch scenario again. If you were to make a bet right now about how the universe might end, the smart money would be on the Big Freeze. It's most likely, given what astronomers have observed, that dark energy will remain a constant. Thinking of the universe ending can induce a feeling of panic. We have a hard time imagining our world ending or even our lives. The default way of life is to fight against death. When someone dies in the hospital, we assume that everything possible was done to prevent death and are outraged if that wasn't the case. Horror films reaffirm the underlying assumption that death is to be feared. Death is so terrible to so many of us, the genre is called horror. We can't imagine anything worse than death. To cope with death, we imagine a future where our bodies are no longer the end of our consciousness. Futurists talk about a time when our minds will simply be uploaded to a simulation. But as much as we want to fight it, death is inevitable, and as best as we can determine from our current understanding of the universe, it all comes to an end. Motion ends, and if time still exists, it'll have no relevance. Is it possible to accept the inevitable without imagining an afterlife or any kind of escape from nothingness? The Greek philosopher Epicurus had an angle that might help. He asks you to imagine what it's like being dead, but you can't actually imagine being dead. Death is an absence of existence. There is no perspective from a view of nothingness. Death isn't an experience, it's nothing to us. You won't feel the pain of absence or nothingness because that would require a perspective. Pain is rightfully feared because it is an experience, but death is no experience. Fearing it is pointless. Why should I fear death? If I am, death is not. If death is, I am not. Further reinforcing this idea is the Roman poet Lucretius. In the 1st century BCE, he insisted that your pre-existence is the same as death. And just like death, we can't imagine what it's like to not exist before we were born. We don't fear our pre-existence just as we shouldn't fear our post-existence. I do not expect that intellectualizing away the fear of death will be entirely effective in getting rid of it, but it can potentially calm the mind somewhat when the fear of death overwhelms too often. In truth, we don't want to be completely fearless of our morality anyway. That would probably be a reckless life that leads to needless harm to yourself and potentially others. And it doesn't address the fear of losing others. This is a painful experience regardless of your perspective. Life is inevitably painful, and one day, the universe will be devoid of it. You, me, and almost everything we know. Unless, of course, despite our most likely predictions, the cycle continues. But I'm afraid that might be wishful thinking or require a leap of faith. If you're struggling with the fear of death or you're grieving the loss of a loved one, I suggest you watch this video. It's helped thousands of people, and I hope it'll help you too. Have you ever looked up at the night sky and pondered about your very own existence? Maybe you were camping out with some friends, or all alone marveling at the big canvas of darkness plastered with countless glowing stars. Well, you're not alone. Looking above and contemplating the sheer immensity of the universe is something humans have been doing since the dawn of time. It's quite magical that recognizing you're part of something inexplicably huge and impersonal can elicit feelings that are so deep, reflective, and personal. Whenever you find yourself lost in these pensive moments, know that the universe, this ancient organism that we were somehow born into, is calling you on a spiritual journey that is in one way or another meant to guide you through your deep and existential emotions and help you find your place in its cold yet comforting grasp. The ancient Stoics understood precisely how immense our human problems could feel. They knew how a bad day at work could develop into a week of aggravation. They knew how a string of bad luck could become a gateway to depression. But they also knew how insignificant our problems really are in the grand scheme of things, and that once we fully understood this cosmic scale, we would truly become free. So if you're having a bad day or you just feel a bit out of sorts, find a quiet place and prepare yourself to witness the view from above for the first time. You're about to embark on a journey outside of your own body, a celestial adventure meant to help you understand the sheer size of our ever-expanding universe, and in the process, your place in it. Because only when you look above will you be able to understand what's within. So take a deep breath and close your eyes. Your journey across the universe is about to begin. Wherever you are right now, imagine yourself slowly lifting out of your body and floating in the vicinity of the room you're in. Observe your surroundings. You're no longer confined to the borders of your own body. Can you see yourself sitting there with your eyes closed, taking deep breaths? Looks weird, right? If you think about it, no one really knows you like you know yourself. People's perceptions of you are based on their own interactions with you. They have their own biases and judgments, and while some of them come close to knowing who you really are, none of them ever fully do. Floating around in your room, you can finally experience your true self. You can observe your body without being inside of it. The room you're in all its familiarity, could very well feel alien to you right now. You may have grown up in this room, spent years developing your sense of self, and yet, as you float around, none of it feels it's genuinely yours. As the abstract feeling of detachment swirls through your mind, you suddenly zoom out to observe the countless houses in your neighborhood or the endless apartments stacked in towering skyscrapers. People just like you wake up every morning and carry on living in the same houses, growing up in the same streets and leading similar lives. It's funny how we could be so physically close to each other and yet know nothing of one another. How many people live in your town or city? How many of them do you really know? What are their dreams and ambitions, their fears and insecurities? Do you think they're that different to yours? We tend to think that our human experience is so unique that no one, not a single person out of the nearly 8 billion of us on this planet, can begin to understand what we're going through. But the truth is, we're a lot more similar than we believe, and that should give us solace in the face of adversity. Look at the houses in your neighborhood, or the buildings stacked elegantly next to each other. They are all the same. As you witness this view from above, your heart will begin to fill with an unexpected warmth as you feel connected to every one of the humans inside those houses. It's like a piece of you lives in every single one of them. A lot of the towns in the US have populations of 1,000, and yet we still call them small. But aren't 1,000 people a lot? Try and imagine that number on a football field or a basketball court. Are these towns still considered small in your eyes? The United States is actually considered a nation of small towns. Out of a population of around 330 million people, data from the past decade shows that 3/4 live in cities and towns with fewer than 5,000 people. So I ask again, is 1,000 small? Continue to zoom out and you see the towns and cities that make up states bound by imaginary borders. Or are they really imaginary? There's around 40 million people living in California, basking in the golden sun of the Pacific Ocean. On the other hand, there are only about 732,000 people living an entirely different life in the cold of Alaska. The life of a Californian is very different from that of an Alaskan, even if both are just humans trying to make the most out of their puzzling existence. Our history has also drawn some real blood-stained boundaries, separating us and forcing us to focus on our differences rather than our similarities. Wars have claimed millions of lives, mostly in the names of ideologies of separation and alienation. As you slowly travel the globe from the American continent, you see how life can develop completely differently despite proximity. Throughout history, many countries fought internal civil battles and subsequently declared their own independence. South Sudan declared independence from Sudan in 2011, Kosovo declared independence from Serbia in 2008, and Montenegro became its own state after separating from Serbia in 2006. Many more have separated and declared their independence, which makes you wonder how defined we are by the countries we're born into. Are you still breathing? Your journey through planet Earth is almost over. You've lifted from your body, away from your hometown, out of your home country, and now you're floating in the atmosphere of our tiny blue planet, perhaps aboard the International Space Station. In 24 hours, this tiny space station orbits our planet 16 times. 16 sunrises and 16 sunsets. Imagine looking at the Earth as you orbit its 40,075 kilometers, or around 25,000 miles circumference. Except for the moon landing, everything that has ever happened in the history of humanity has happened on this planet. Everything we've ever experienced, every joy, every disappointment, every love, every broken heart. Our entire human existence is presently confined to this rotating globe floating in the vastness of space. And as it rotates at 16,075 kilometers per hour, time passes and washes away all that ever was and makes room for whatever there is to come. Our planet has existed for 4.5 billion years, but us modern humans have only been here for around 200,000 years, and civilization as we know it is only around 6,000 years old. You and me, if we're lucky enough, will only get to experience around 80 more of those years. Everything that has happened before and everything that will happen after, we can only imagine. The burden of our existence is nothing but a speck of dust in the cosmic hourglass. Looking at Earth from above could be daunting. Astronauts that live on the ISS almost always come back to Earth with a fundamental understanding of what it truly means to be alive, and what matters most in life. Take another long and deep breath. Let your lungs fill with the magnitude of what you've already experienced and what you're about to experience. You're going to journey further into space, deep into our solar system, and then into uncharted territory where no human has ever traversed. Leave all your human preconceptions behind and open your heart to the expanding universe. As you finally break free from the Earth's atmosphere, imagine yourself floating further to the edge of interstellar space, looking at our solar system as a whole. 8 planets circling around a glowing star. Each one of these planets has its own unique story, from Saturn's ringed beauty to the massive bulk of Jupiter and its great red spot big enough to engulf the entirety of Earth. But even Jupiter's incredible mass holds no candle to the centerpiece of our glorious solar system, the Sun, the star that holds our collection of planets together. Our Sun is 109 times wider than Earth and makes up 99.8% of our solar system's entire mass. Put everything you've experienced in the scale and then compare it to the sheer magnitude of our glowing star, and let it sink in for a second. Let's take a step further and slowly leave the safety of our solar system. Observe as the Sun itself becomes a small particle, barely visible from our astronomical vantage point. You look around you and notice the countless other stars, billions of glowing specks everywhere you turn. There are more stars in the universe than there are grains of sand on Earth, more than 10,000 stars for each grain, in fact. Most of these stars have planets orbiting around them, just like our solar system. If the primordial soup that spawned life on Earth managed to replicate on one of these countless planets, would it be similar to life as we know it on Earth? Would they wonder about their existence the same way we do? Would they understand how small and insignificant their problems are in the grand scheme of things? Imagine alien civilizations fighting through their own existence just like you and I. Imagine the struggle to exist in the universe every day. Planets that harbor life, that orbit stars, that make up galaxies that float around alone in space. You are now leaving the Milky Way and venturing further out into the still and silent darkness of the universe. Everywhere you look, there's a galaxy waiting to be explored. A galaxy that could harbor a star, that might have a planet that somehow managed to produce life against all odds. One more deep breath, and you're now looking at the entire observable universe. One big organism that is at least 92 billion light years wide. Now that you've been able to observe the universe as a whole, it's time to slowly bring it all back in. Let's find the Milky Way among the hundreds of billions of galaxies out there. Let's find our Sun among the 100,000 million stars in our home galaxy. We're finally back in the solar system, passing from Neptune to Saturn to Mars, and finally Earth. You jump from the ISS and burst through the atmosphere and then cross the imaginary borders that are meant to separate us. Find your country, your state, your street, and then your home. Finally look at yourself breathing, taking all that experience in. Take one last deep breath and open your eyes. Next time you're feeling down or the world seems to be taking too much of a toll on you, contemplate your existence and remember this moment, this feeling, this experience. Let it remind you that whatever is weighing you down is only temporary. A minor setback in the grand cosmic scale. The entire universe, every electron, proton, atom, every star and galaxy, was born out of a singularity that brought about our whole existence. The Big Bang, an isolated moment in space and time, created something out of nothing. For eons we didn't know much about the universe, but through advancements in science and technology, we're now able to travel back in time, right to the point just after the Big Bang to finally piece together its entire story. And in the next 10 minutes, I'll be sharing that story with you. To be able to understand the history of our universe, we have to start at the beginning of time, and time itself was born with the Big Bang. Contrary to what its name might suggest, the Big Bang was not an explosion. It can more precisely be described as the rapid expansion of space and time in all directions, releasing immense amounts of radiation. In 1964, two Americans, astronomer Robert Wilson and astrophysicist Arno Penzias, stumbled upon a cryptic message traveling from the moment of creation itself. Their antenna in New Jersey picked up an odd buzzing sound that puzzled them. After eliminating all possible sources of interference, Wilson and Penzias figured out that they had just discovered the cosmic microwave background, or CMB, the thermal echo of the universe's explosive birth, and the most crucial piece of evidence for the Big Bang. Thanks to this ancient message, we know our universe came into existence 13.7 billion years ago, and it immediately began expanding at an exponential rate. This is known as the inflation epoch. When it was less than a blink of an eye old, like a billionth of a trillionth of a second old, our universe underwent an astounding growth spurt faster than the speed of light. Within a fraction of a second, it doubled in size at least 90 times. But as it expanded, the energy released became more diluted. In just 3 minutes, the universe had cooled down enough to allow the first particles of matter to form, and the first light elements were created. Neutrons and protons began colliding with each other and formed hydrogen, helium, and lithium. Though the particles were formed, the intense heat from the moment of creation made it too hot for light to shine, and so our universe was plunged into a cosmic dark age for hundreds of millions of years. Space was desolate and devoid of any planets, galaxies, or stars. Then the age of reionization began, and light finally emerged from the darkness with the birth of the universe's first stars, known as population 3 stars. These are believed to be made of the only ingredients available in the universe at the time: hydrogen, helium, and lithium. These stars are time capsules rich with information about our universe's earliest days, and with the James Webb Space Telescope, we can now look into them with greater detail than ever before. About 1 billion years after the Big Bang, galaxies began to appear, and there are 2 theories on how they first came into existence. The first suggests that big clouds of gas and dust collapsed under their own gravitational pull, allowing stars to form and eventually galaxies. The second, which has gained momentum in recent years, suggests that galaxies formed when small lumps of matter kept clumping and swirling together until they eventually grew to the size we're familiar with today. Our galaxy, the Milky Way, is roughly 13.6 billion years old and contains between 100 to 400 billion stars, and spans about 100,000 light years across. Astronomers are still working on charting the spiral structure of our galaxy. Although using infrared images from NASA's Spitzer Space Telescope, we've discovered that it is dominated by 2 arms wrapping off the ends of a central band of stars. Stars and galaxies are still being created to this day, and astronomers estimate that there could be as many as 2 trillion galaxies spiraling through the black ocean of our universe. 4.5 billion years ago, a dense cloud of interstellar gas and dust kept swirling together. As gravity pulled more and more material into the center, the pressure in the core was so great that hydrogen atoms began to form to make helium, releasing immense amounts of energy. This process eventually gave birth to the star we see every morning when we wake up, our sun. Once the sun was formed, the matter surrounding it clustered into spheres and fell into its gravitational pull, creating the planets in our solar system. The giant planets, Jupiter, Saturn, Uranus, and Neptune, were the first to circle the sun. As it began emitting its light, the smaller planets Mercury, Venus, Mars, and our very own Earth formed. Our planet just happened to orbit the sun in what scientists call the Goldilocks zone, the perfect temperature and distance from the sun to allow for liquid water to exist. Somewhere between 60 to 175 million years after our solar system was born, a Mars-sized planet collided with Earth, and the post-impact debris morphed together to give us our moon. Talk about upcycling. Life in our universe seems to be far from inevitable. Everywhere we point our telescopes end up seeing the same thing: bright nebulae, star clusters, and ominous galaxies that all look desolate and lifeless. But when it comes to our home planet, the story is very different. Life on Earth first appeared 3.7 billion years ago, but how it sprung into existence is still a hot topic of debate. Many believe the first living organisms were microscopic microbes that left signals of their presence in rocks. Others think life started in a primordial soup deep in the ocean through vents in the seabeds, where the interaction between water and rocks provided enough chemical energy to allow the first unicellular organisms to emerge. Whichever side of the argument you're on, though, the one thing that's certain is that the Earth was teeming with life long before we showed up. We came onto the cosmic scene just around 6 million years ago. A long time for sure, but minuscule when compared to the 13.7 billion year lifespan of the universe. Although our early ancestors joined the party late, we've moved quicker than we could have ever imagined. In just a short span of time, we've gone from hunter-gatherers to cosmic explorers preparing to create a base on the moon's surface. Our telescopes now allow us to see further than we've ever been able to before, and our questions are bigger than we've ever dared to ask. But even with all the tools available to us, there are things in the universe that are still shrouded in mystery. Around 85% of our universe is made up of a mysterious substance that we have never seen. In 1933, Swiss astronomer Fritz Zwicky measured the visible mass of a cluster of galaxies and found that it was too small to prevent these galaxies from escaping the gravitational pull of the cluster. Zwicky concluded that something must be acting like glue holding the cluster together. That mysterious substance we now describe as dark matter, a completely invisible material that fills up our universe and acts as an astronomically potent superglue. Without dark matter, the behavior of stars, planets, and galaxies would just not make sense, and our universe would not have evolved the way it has. And then there's dark energy, the strange force that is pulling our universe apart at an ever-increasing speed. Just like dark matter, dark energy is invisible, but its powerful effects are largely felt.
And liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
In 1920, Edwin Hubble discovered that the universe is not static, but is still expanding. And in 1998, the telescope named after the astronomer proved him right. And even more, that the universe was expanding at an accelerated rate. We have since discovered that dark energy is the reason for this expansion, and also why stars and galaxies recede away from each other. While much about the formation of the universe and its evolution has been theorized and plotted on the cosmic timeline, there are still enduring questions to be answered. With telescopes like Webb, we'll continue to hunt for the elusive dark matter, as well as look back into our universe to understand the evolution of stars and the formation of galaxies. Our quest also includes searching the cosmos in hopes of finding life forms to share our existence with. During this search, we've discovered exoplanets that orbit around a star outside of our solar system. Based on NASA's Kepler Space Telescope imagery, we can confidently assume that every star in the universe has at least one planet orbiting around it. In our galaxy of hundreds of billions of stars, it's believed that there are trillions of exoplanets. Yet we've only discovered around 3,900 of them. A little more than 4 light-years away, Proxima Centauri is the closest of these exoplanets, but scientists have their eyes on bigger things with the TRAPPIST-1 star system. This star system is home to 7 planets, all roughly the size of Earth, orbiting around a red dwarf around 40 light-years away. Our space telescopes, ground telescopes, and best scientists are working to try and understand whether any of these planets have the right ingredients for life to spring into existence. I made an entire video on what it would be like to live on one of these planets, the only one that scientists believe could possibly hold life. Whether we succeed in this mission is a story that will be written in the universe's future. One that will either propel us forward towards the understanding of the cosmos and our place in it, or will leave us pondering our lonely existence. Our universe is currently 93 billion light-years wide, filled with trillions of galaxies, and 1 septillion stars, that's 24 zeros, and it's still expanding through the vastness of space. Sometime in the distant future, it's estimated that our Milky Way will collide with the neighboring Andromeda galaxy. Because though the universe is expanding, galaxies are receding away from each other, and the proximity of the 2 galaxies will make the collision inevitable. Don't worry though, we'll be long gone before that happens. 100 billion years into the future, galaxies will disappear, and eventually, our universe will be populated by black holes ravenously eating away all that is in their way. As a new dark age sets upon our universe, astronomers believe that its fate is bound to end the same way that it began. With time, space will begin contracting again. The universe will shrink in size until one day, it devolves back into the singularity that started it all. A sort of big crunch reversal that'll bring things full circle and leave behind an emptiness aching to be filled. And then, who knows? Bang. In the year 1609, Galileo pointed one of the first telescopes ever created up at the heavens, and what he observed sparked a revolution of curiosity that has been central to every single human generation since. Galileo saw mountains and craters on the surface of the moon, the arm of our Milky Way galaxy arching across the sky, and an endless universe riddled with countless stars. The mysteries of outer space were boundless, and the journey towards discovering them had only just begun. Over 400 years later, and our obsession with the enigma that is space has only managed to intensify, fueling many great technological advancements that have made our ever-expanding universe seem smaller and its boundaries closer than ever. On the 25th of December 2021, NASA launched humanity's most powerful telescope yet. More than 30 years in the making, $10 billion spent, a successful launch, 50 intricate outer space deployments, and a distance of over 1.5 million kilometers traveled from Earth, the James Webb Space Telescope has finally delivered its first full-size images of our universe, marking an era of space discovery that promises unique and unprecedented views from across our own solar system to the very heart of the universe. The James Webb Space Telescope,
JWST for short, has been designed to look more than 13.5 billion years into the past to study the farthest and oldest regions of space, peering back into the early days of the universe. Its aim is to look at the first galaxies that started forming and emitting light right after the Big Bang. It's no wonder that scientists often refer to telescopes as time machines. In them lies the power to see what our universe once was, and perhaps answer one of humanity's most perplexing existential questions. How did we get here? And right now, Webb is our best chance at finding an answer to that question. However, to fully understand what makes Webb so special, we have to travel back in time to the year 1990, when the Hubble Space Telescope was launched. The Hubble Space Telescope embarked on a mission similar to Webb's. Its purpose, just like Webb's, was to study the universe like it's never been studied before, and to bring us closer to understanding our existence and our place among the stars. Over the past 30 years, Hubble has brought us images of galaxies we never knew existed, star clusters, and nebulae like we've never seen before. These images helped illustrate how in the early days of our universe, just millions of years after the Big Bang, cold clouds of gas and dust evolved into swirling, coalescing galaxies teeming with stars. Sadly, that was just how far Hubble could see. In order to observe how these first galaxies were born, we needed a bigger telescope, one that wasn't just more powerful, but that could also operate in the infrared. So just a few years after Hubble was launched into space, scientists began working on the next big telescope. Today, Webb is 100 times more powerful than Hubble, and its ability to observe infrared light opens up a new universe of possibilities. Literally. Ever since Edwin Hubble discovered that the universe is expanding, we've known that galaxies have been receding at faster and faster speeds. Light from these galaxies is stretched to longer wavelengths as it travels through space, which is why they're only visible through infrared. Hubble, the telescope, is only able to see light on the visible spectrum, which means it's limited in the amount of information it can fetch us about these earliest galaxies. But with Webb, we finally have the ability to observe them. To detect these infrared waves, Webb traveled more than 1.5 million kilometers away from Earth's warm atmosphere, to a very cold region in space that is protected from our planet's infrared radiation. Built into this telescope are huge sun shields as big as the tennis court, that protect it from the rays of the sun and help keep its temperature at minus 233 degrees Celsius, so it can be cool enough to detect infrared radiation from the early days of the universe. This is the first time in history of our species that we've been able to look at our universe with such depth and detail. And the first images NASA released on July 12th are proof that we've entered a new space frontier that is bound to bring us closer to understanding our place in this ever-expanding universe. Let's begin our journey back in time with the closest image Webb has taken. This is called the Southern Ring Nebula. It's a planetary nebula in our own Milky Way galaxy, 2,000 light-years away. Despite its name, a planetary nebula doesn't have any planets. The name is simply inspired by its round structure. A nebula is clouds of dust that are thrown out by the explosion of a dying star. You can see enormous clouds of gas thrown out by this red giant in the center of the image. This image utilizes Webb's near-infrared camera, or NIR cam, which looks at the shortest infrared wavelengths. When we switch to its MIRI, or mid-infrared instrument that can observe longer wavelengths, you can actually see that it gives us an unprecedented look into the heart of this nebula. Right here, you can actually see two stars at the center of the system, with the dimmer one being a white dwarf at the tail end of its life, and the brighter one, a red giant, at an earlier stage of its dying process. The pair of stars are locked in each other's orbit in a cosmic embrace, which leads the dimmer star to spray ejected material like a sprinkler, resulting in these jagged rings. Stars are critical to life as we know it. With Webb's powerful mirrors and its ability to peer behind the thickness of gas and dust, we'll be able to study the death of stars like we've never done before. This could give us a greater understanding of the chemicals and the elements that are discharged from stars as they evolve through time, and whether these components are the building blocks that are needed to spawn life as we know it back on Earth. But the birth of stars is just as important as their death. This image of the cosmic cliffs in the Canary Nebula, 7,500 light-years away, offers a breathtaking view of the clouds of gas and dust actively coming together to form new stars. This is one of the most active star-forming regions in our galaxy, a star nursery that could give us tremendous information on this creation process. When we switch to the MIRI once again, you can see the infant stars behind this ethereal cloud of dust. Being able to see what is behind their cosmic clouds is incredibly important when we look at galaxies as a whole. It can enable us to estimate the total mass of stars in a galaxy with more accuracy. Speaking of galaxies, 300 million light-years away lies the tightest galaxy grouping we've ever discovered. These 5 galaxies are called Stephan's Quintet, and they are all bound to crash into each other and eventually merge. Actually, 2 of them are already in the process of doing exactly that. This image of Stephan's Quintet is the largest of Webb's initial images. It might not look like it at first glance, but what you're seeing here is actually a composite of over 1,000 images made up of over 150 million pixels when combined together. Zooming in on any part of this picture will show you hundreds, if not thousands, of galaxies waiting to be discovered. What's even more fascinating is that when we switch to the mid-infrared instrument, we can spot never-before-seen details of Stephan's Quintet. That very bright structure in the uppermost galaxy is actually a supermassive black hole, 24 million times the size of the Sun, and actively increasing in density while emitting more energy than 40 billion suns put together. Just pause and think about that for a moment. These new images provide us with valuable insights into galactic interactions that may have driven galaxy evolution in the early universe. The early universe, Webb's primary mission. This is what is called a deep field image. Deep field is a long-lasting observation into a particular region of space, intended to collect light from the faintest, furthest objects. Peering 4.6 billion years into the past, this image shows the galaxy cluster SMACS 0723 at its center, alongside shimmering stars, warped light trails, and thousands of extremely distant jewel-like galaxies. It's the deepest and sharpest infrared image of the early universe we've had so far. But despite its magnificence, what's most interesting about this deep field is the warped light trails around the galaxy cluster's edges. This galaxy cluster is so massive that it warps space-time, and ultimately the light of stars and galaxies located billions of light-years behind it. This is called gravitational lensing, and acts like a cosmic magnifying glass, bringing the light of galaxies almost 13 light-years away, potentially making them some of the oldest galaxies we've ever observed. Without a doubt, these early images are breathtaking and already showcase the huge capabilities of Webb. But taking pretty pictures isn't the telescope's only superpower. It can also study the atmosphere of planets. For a while now, we've been searching for exoplanets, which are planets outside our solar system, orbiting around a star similar to our Sun. We've discovered about 5,000 of them so far, with our main goal being able to find one that's hospitable to life, and ultimately finding some of that life. When analyzing the atmospheres of exoplanets, we look for elements such as methane, oxygen, or nitrogen, ingredients present in our own atmosphere that could signify the presence of life on these planets. So far, the universe hasn't offered us any signs of life. However, this graph captured by Webb of the hot gas giant exoplanet WASP 96b could be our first step towards locating some extraterrestrials. The observation reveals the presence of a very specific gas molecule, water vapor. While Hubble analyzed numerous exoplanets' atmosphere over the decades and detected water in 2013, Webb offers a more detailed observation, and a giant leap forward in tracking down habitable planets beyond Earth. This image is only a glimpse of Webb's massive ability to capture precise atmospheric elements hundreds of light years away. We've always wondered whether life exists beyond Earth, and Webb could be the tool to help us answer this question and change the meaning of our existence forever. The James Webb Space Telescope has only begun its journey, and the road ahead is still long and daunting. Analyzing the universe's origins, understanding the birth and death of stars, discovering distant galaxies, and finding exoplanets are only just the beginning. The truth is, looking more than 13 billion years into the past is bound to raise more questions than we could ever imagine, but it also has the potential to answer questions as well, some of which we've been asking since the days of Galileo, and even new ones we never knew we had. When Galileo raised his telescope to the sky and looked at the craters on the moon, he acted on an almost instinctual human curiosity that has been with us ever since the dawn of time. More than 400 years later, the same curiosity is bringing us even closer to our cosmic background. Earth is only a small stage in the cosmic arena, and with the beginning of a new era in space discovery, we now know that more than we ever did before. There is no doubt that in the upcoming years, Webb will bring the universe even closer to us and help us know more about the reality of our cosmic existence. So whenever you find yourself looking up at the night sky and its beautiful stars, remember, somewhere, something incredible is waiting to be known.
The universe was really small and dense at one point, and then all of a sudden it wasn't. But wait a minute. Let's rewind and figure out what happened right here. This is because of two things, entropy and dark energy. To put it simply, entropy is the measure of order in the universe. It's a measure of uncertainty or randomness. The higher the entropy, the more disorderly the universe is. It's like your bedroom. A messy room is a high entropy state because it's much harder for you to be certain of where any specific object could be. For example, that sock you lost last week. But once you clean everything up and make it neat and orderly, it's much easier to be certain about where an object will be. This is entropy in a simple nutshell. But why is it important? Simply put, it could be what causes the end of our universe. Before we get to the end of the universe, we need to discuss what events will occur between now and then. This video is much like a sequel to a video I made recently called What Will Happen in 1 Billion Years. If you haven't seen it, I suggest you watch it. If you do, this video will make more sense. Anyway, right now, the Milky Way galaxy and the Andromeda galaxy, the closest galaxy to our own, are racing towards each other at a speed of about 110 kilometers per second. But in 4 billion years, the night sky will look the most beautiful that it has ever been. The collision of galaxies sounds like a really big threat, but actually our solar system will most likely remain intact. Due to the huge sizes of our galaxies, this most likely won't affect anything inside our immediate neighborhood. Andromeda is 260,000 light years across, while the Milky Way is only about 100,000 light years. And I say only 100,000 light years like it's nothing. But at our highest estimate, our solar system is only about 4 light years in diameter at most. When our galaxy collides with Andromeda, the night sky will be filled with gas clouds and nebulas forming new stars. Assuming there's still life on Earth or in our solar system at this point, because galaxies are mostly empty space, we only need to be worried about avoiding any object within light years. Oh, it may be our own sun. In about 5 billion years, the hydrogen in the sun's core will be completely exhausted and will leave what is called the main sequence, a place where dwarf stars who aren't quite giants live. And this is when the sun will begin to expand, which isn't exactly good for any life on Earth. The Earth, Moon, and according to many scientists, maybe even Mars will be swallowed whole by what is now the red giant sun. But there's an upside. This destruction may cause Titan, one of Saturn's moons, to have conditions extremely similar to what Earth's are today, meaning that we could possibly have living conditions on Titan. But even then, things aren't too safe. Because in the year 22 billion, the first universe-ending scenario comes into play. The Big Rip. Low entropy states require work to achieve, so naturally everything, even on the scale of the universe, seems to tend towards disorder. You can tie this in with a Big Bang. The universe was in an extremely low entropy state in the beginning. All the matter and energy in the entire universe today was compacted down into one minuscule point. Since then, the universe has been expanding, cooling down into a higher entropy state, a more disorderly state. You would think that over the billions of years since the universe's beginning, the universe's expansion would slow down, but actually, it's doing quite the opposite. It's speeding up. This is due to dark energy. We have known that the universe's expansion has been speeding up for decades, but the reason why remained unknown, so we call it dark energy. Right now, the idea is that dark energy will continue expanding the space between galaxies, and that large structures in the universe like galaxies, stars, planets, and even molecular bonds will be strong enough to stay held together. This is due to forces such as gravity and the weak and strong nuclear forces. If this is true, then dark energy will never be able to become strong enough to pull these objects apart. However, there is a possibility that it might not work like that, and this is a problem. There is a bit of experimental evidence that suggests dark energy may get even stronger over time. If this is true, then eventually, in billions of years, the distances between objects won't matter. Anything and everything will be torn apart. First, the galaxies themselves will be ripped apart since the space between objects in a galaxy is so massive, like we talked about with Andromeda. Then, the star systems will be torn apart, our solar system. Then, the stars themselves. And then the planets that even inhabited these solar systems. And if dark energy is strong enough, if it keeps getting stronger and stronger over time, then even objects that are held together by stronger forces, molecular bonds that are held together by the strong and weak nuclear forces, will be shredded apart by the now overpowering dark energy. Nuclei themselves will be ripped apart from their atoms, and this will result in a universe with nothing left. Everything has been ripped apart, down to the very last atom. That is the Big Rip. When dark energy causes space itself to expand faster than the elementary particles that make it up, the universe would just be a sea of empty particles that would never be able to interact with anything ever again. But keep in mind, this is theoretical and based off of only a few scientific experiments. So let's say that doesn't happen. What will happen next? Even if the universe isn't violently ripped apart by dark energy, it still exists. Or at least we think it does. And it is still causing the universe to expand. So by the year 100 billion, dark energy will have caused the entire universe to expand so far apart, even at the speed of light, we won't be able to see or interact with any galaxies that aren't a part of our local group. Out of an entire universe made of hundreds of billions of galaxies, in 100 billion years, we will only be able to interact with a measly 54 of them. And when you do the math, it's kinda sad how little of our universe we'll be able to interact with. In 1 trillion years, these galaxies that we call the local group may collide with one another, back to back to back, until eventually the local group is one mega galaxy. And as cool as that sounds, it's kinda lonely in a way. For any life living in the galaxy, that's it. That's all you'll ever know. And around this time, all the gas clouds that are necessary to form new stars and solar systems will begin to exhaust themselves until eventually there are no new stars being born. All the stars that are alive then will be the last of their kind, until the very last star in the universe fades away into nothingness. And eventually, the universe will go dark. Which leads us into our second doomsday event for the universe, the Big Freeze. In 25 trillion years, the last shining star in the universe will either fade out or be swallowed into the supermassive black hole at the center of its galaxy. In 10 to the 30 years, black holes will begin to eat the remaining neutron stars and dwarf stars, while the black holes themselves decay away over trillions of years due to Hawking radiation. In a Google years, that's 10 with 100 zeros after it, a black hole with the size of 20 trillion solar masses, that is a black hole with a mass of over 20 trillion suns, will finally decay completely due to Hawking radiation. And then, there's nothing. In the immense universe over this unreal timescale, there is practically no activity whatsoever. The only activity is random subatomic particles popping into existence for a brief second before they disappear forever like the rest of the universe. That's all there is. The universe has seemed to freeze to a stop. Entropy is at its highest state. The universe is dead. Except, maybe it isn't. In 10 to the 10 to the 10 to the 56 years, which by the way is a number so big that when I sat down and wrote the script for this video, and even now, I couldn't even figure out how to physically write that number down. I tried to figure out a way to put this into scale, but I can't. It's 10 with this many zeros after it, which honestly just makes me more confused. If you were to try and fully write out that number, with all the zeros and everything on one line on a really, really long piece of paper, that piece of paper would be so large that it wouldn't even be able to fit within our observable universe, due to the sheer length of that number. In that many years, due to those subatomic particles we mentioned, combined with quantum tunneling, a phenomenon where particles seemingly instantly teleport between locations, even faster than the speed of light, there is a chance there could somehow be an extreme random entropy decrease at an extremely specific point in the vastness of the universe, where all subatomic particles in the universe quantum tunnel to the same exact location at the same time. This would result in a new Big Bang, a new universe, or maybe new universes. Earth and civilization as we know it has come a long way in the past 200,000 years and has experienced a multitude of changes in that time. The human species has only existed for a mere